So those are the aims then. You get an assignment to do at the end of this session, plus there's an exam at the end, and there's an example of a Laplace transform type question in there. So they'll appear as an assignment and also in the exam. You're going to use the Laplace transforms to analyse a circuit. So the aim of the assignment is to actually have a circuit and to analyse it using some software. What's the name of the software, Mike?
Multisim.
Multisim, thank you. And then also to model it using the Laplace transforms on autograph until you get two printouts, one showing a multisim model of the circuit, one showing the autograph mathematical function which should match, and then finally set up the electronic circuit itself and then see what we get using picometer. What's it called? Picoscope.
Well, the PC-based oscilloscope.
Okay, so that will capture the signal, and then we can compare them. Okay, so that's the plan. So we're going to use these Laplace transforms to analyze circuits like this. So I'll put one on the board. So we put the capacitor and inductor and a resistor in a loop like that with a switch. We fully charge the capacitor by putting the supply across it, charging it up, then removing the supply, so the capacitor just sitting there charged, waiting for you to close the switch, and then it will discharge. So, if we were to plot a graph, a charge against time, as this capacitor discharges, it's going to start off at an initial value Q0, and then charge is going to flow out of the capacitor. Split this over here so I can. We could just build a circuit with certain values of R and C in it, close the switch, and then observe what happens. And you'll do that with a particular circuit. However, it would be useful to be able to analyze the effects on the circuit of changing the values for the capacitor, the resistor, and the inductor. So we could usefully come up with some sort of model to describe how this thing's going to behave. And then we can change the values of L and C and R and see the effect. And also, if we want a particular effect, assign values to L and C and R to give us an effect. So it's useful to be able to come up with a mathematical model to describe the circuit rather than just play around with it and be sort of reactive rather than proactive. How do you think the charge will behave? Sort of speed.
Possibly a curve, possibly something curve.
Right. What sort of curve are you describing in the air there, Mark?
Half a parabola.
An exponential.
Yeah.
An exponential change. Yes, some sort of exponential decay. Is this capacity?
Yeah.
Is this capacity of this change? Yeah. Okay. Will the inductor have an effect? Those electrical engineers amongst you? Probably not. Yeah. I wouldn't mention it didn't have an effect, would I?
Yes, it will.
Yeah. Why would it, Andy?
Because it's to do with lagging and leading of the AC sine wave.
It's not a sine wave here. We've just got a fully charged capacitor, then we're closing the switch and the capacitor discharges. As the charge flows through the inductor, what's going to happen? What do inductors do?
They sort of stop the charge from going through until it reaches a certain point.
They create a back EMF, don't they, which sort of tends to oppose the rate of change of flow or current through it. And so that might well have an effect on the circuit. So we sort of guess that there'll be some sort of, I mean, you know, the capacitor will discharge, but will it be a straight discharge like that, or is there some sort of other effect? And what's the rate at which this is going to happen?
That will depend on the value of the resistor.
Yeah, that's right. Certainly depend on the value of the resistor, probably on the value of the capacitance, and also the inductor. Okay, so we need a model, and the model is going to come up with a picture that we can, a function that we can draw in something like autograph, and end up with a function. Right.
Can I borrow that a bit? I can just do the lessons.
Yeah.
No, you can't. That's what
Sorry, mate. Don't get me worried.
So we come up with this picture. That's what we're after. Okay? So this function that we're going to come up with allows us to describe how this circuit's going to behave. And one thing you can always do with a function is to plot it. So we're going to do that in a bit of software and see what it looks like. And that will describe how the charge varies with time in this circuit. So we need a mathematical model. So a mathematical model involves almost invariably some sort of equation, differential equation usually, that we need to solve. So a mathematical model that involves a change and what branch of mathematics pops into your mind as soon as you see the word change? Calculus, right. A mathematical model that involves change almost invariably means solving a differential equation. And we did look briefly last year at mathematical models and differential equations, and particularly solving differential equations by separation of variables. But they were more straightforward differential equations than the one we're going to have to cope with now. For this circuit, the differential equation is this. There.
What's the bit at the front?
L
Right.
for the inductor.
Right. Okay.
Yep.
Right.
L d2q by dt squared, R dq dt, and q over c.
That little key for the charge.
Yeah. It turns out, if we just analyse this circuit for a second, or this differential equation for a second, rather than see how it applies to this circuit here. Starting from the right-hand one, well, for a start off, if we look at this circuit initially, then the voltage, if I wanted to actually observe what's going on across, how is the voltage changing across the capacitor, I'll probably put some sort of CRO across the capacitor, that's just observe it. And CROs don't measure charge, they measure voltage. But luckily for us, there is a direct relationship between the charge on the capacitor and the voltage, Q equals CV. It's an equation you're probably familiar with. So the voltage equals Q divided by C. So this CRO measures the voltage. If we know the voltage, we just multiply that by the value of the capacitance and we've got the charge. So we can plot a graph of charge against time. But of course, we're actually going to be measuring voltage. So V equals Q over C. And if we go back to this original differential equation, Q over C, so this stands for the voltage across the capacitor. Now, what's another term for the rate of change of charge with time?
Okay.
No, in a circuit, the rate of change of charge with time, the rate of flow of charge, what do we call that? Current, yeah. And so, dq by dt equals the current. And IR, Ohm's law, is a voltage. So this is the voltage across the resistor, okay? Because it's IR. This part here is the current, I. Now this is the rate of change of current. I'll just talk about that for a second. d2q by dt squared means the second differential. So the first differential is dq by dt, and that gives the current. So if I differentiate the current, that's the same as finding the second differential of the change. So d2q by dt squared is the same as di by dt, effectively. It's the differential of the current, or the second differential of the charge. And if you think about knowledge of inductors, the back EMF that's induced equals the inductance multiplied by the rate of change of current. And so this is actually a way of expressing the voltage across the inductor. So what we're actually saying is the voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor equals 0, which you might remind us this morning is Kirchhoff's law for voltages in a loop. There the voltage is not ever at 0. So all we've done here is write an expression for the voltage in terms of charge, across the inductor rather in terms of charge, the voltage across the resistor in terms of charge, and the voltage across the capacitor in terms of charge. Why have we done it all in terms of charge? Because we want to end up with a function that tells us about the charge. So we need all of these things in terms of charge, and that's exactly what we've done. And we end up with an equation. We know it's an equation because it's something equals something, something equals 0, and it's a differential equation because it involves a differential, dq by dt, and because it also involves a second differential, it involves second order differential equation. So it's a second order differential equation that we're going to try and solve. So, the solution to this second order ordinary differential equation, as it's called, ODE for short, gives a function qt, which describes how the charge varies with time in this circuit. Sorry? Ordinary differential equation. We're only going to be coping with ordinary differential equations. They're differential equations that have only two variables, the dependent, which in this case is the charge, and the independent variable, which is the time. Okay, so we've got our differential equation, here it is. And we're going to try and solve it. To give us a function which describes how the charge varies with time in the circuit. What this part of this course I'm doing with you now is all about finding the solution. Is how we solve this and end up with this function. Okay? And the way we solve it is to use Laplace transforms. We're going to use Laplace transforms to solve, to find the solution. For this example, for this circuit here, I'm just going to present at this stage what the solution is so we can have a look at it. Because it's probably one of the more difficult ones that you might use the Laplace transforms to solve. And so maybe at the end, when we've gone through the maths that's required for it, you might also have to look at it. But we'll, in the main, be looking at slightly more straightforward circuits in this, even though this doesn't look that awkward. It's the fact it's got a capacitor, resistor, and inductor in it that makes it a bit more difficult to solve. But it is solvable, and we can look at it using these Laplace transforms. So now let's just have a look at the solution. So for our circuit, the solution turns out to be, or for this example, the solution is, it's worth looking at, because it's an interesting solution, which is why I picked it. Okay, let's check we've got this right. where alpha equals R over 2L. So that's how alpha relates to the actual circuit, where R is resistance and L is inductance. And omega squared turns out to be 1 over LC equals 1 over LC minus alpha squared. Not an obvious solution to this equation, is it? Certainly isn't. It's difficult to see how you get from that original differential equation to this solution.
What's the J?
That's just a colon, a semicolon.
Sorry?
Yeah.
Sorry,
Yeah. I thought I was writing it. That's a bit of a strange thing to do.
yeah.
Yeah. Yeah, yeah.
Oh, God, man.
Got no keys on.
Not yet. Okay, so let's have a look at this solution then. Okay, we're going to plot it in a moment on autograph and see what it looks like. Because remember, this solution is the function that will describe this circuit here. So that's going to give us this trace here. If we look at it, it's got an exponential part to it. Right? So you're talking about it have an exponential decay. You can tell it's a decay. There's a minus sign here. But that exponential decay is also multiplied by some sort of oscillating part to it. Okay? So it doesn't look as though it's going to be a straight decay. There's some sort of oscillation involved with it too. Those of you who've done some work on electronic circuits and have done some work with inductors might want to suggest why that sort of oscillation might occur. Hold that question in your mind. Let's have a look at the function, and then you might be able to come up with some ideas. I don't know how much of this sort of stuff we've done. So let's have a look and plot this function. Before we do, though, if we look at this part of it on its own, if t gets very large, what's going to happen to e to the minus alpha t?
It's going to get very, very small.
E to the minus, let's have a look at this for a sec. For large t, large time, long time, e to the minus alpha t, what does minus mean?
Okay.
Yes, but in terms of indices, 1 over e to the alpha t. As t gets very large, what's going to happen to 1 over e to the alpha t?
Yeah.
If you get smaller and smaller, I heard someone say yes, and approach 0. Okay? So this 1 over e to the alpha t tends towards 0 for large values of t. So if we look back at this, for large values of t, that's going to tend towards 0, and anything times 0 is 0. And so, eventually, this charge is going to be 0, which is what we might expect, isn't it? Okay? If we leave this circuit going for long enough, the charge will disappear, the capacitor will discharge. So if we leave the circuit for long enough, Q will fall to 0. i.e. the capacitor discharges, which is what we would expect. Capacitor discharges. From where to where, Mark?
From that to that.
What, from the differential equation? Oh yeah, exactly, that's the point, and that's where the Laplace is implemented. Don't worry about that. Yeah, I've just sprung this solution on you, and it's certainly nowhere near obvious how you get to there from the differential equation. But there it is. You have to take my word for it that is a solution. And we can see that one or two things about it, which is why I've introduced you to it, because I want to look at it and see why we do these things. First thing to see is, as we've noticed, is the large values of t, that tends to 0, so the charge tends to 0. But this function now allows us to ask questions like, well, what sort of times we talk about? If we leave it long enough, how long before the charges will drop to 0? How long before the circuit? And it allows us to look at what's going on the instant we turn on the switch. So, going back to this here again.
When t equals 0.
Yeah, at t equals 0, we close the switch and things start to happen in the circuit. Eventually, the charge is going to drop to 0. So we say the steady state for this circuit is 0 charge, nothing eventually. But what's going on between closing the switch and this steady state is called the transient period. And so, by analysing this circuit and looking at this function, what we're actually doing is looking at the transient period of this function. It's called transient analysis. And it's important to do that sort of thing because when you first turn circuits on or first turn circuits off, because of the capacitors and inductors in the circuit, things could happen, like this, that we're going to have a look at, which might or might not damage some component in the circuit. So you want to know what's going to happen when you turn it on before you reach its steady state, transient analysis. Okay? So if we leave the circuit for long enough, Q will fall to 0, the capacitor will discharge. The function allows us to analyze the circuit during the transient period before a steady state is reached. And that's called transient analysis, for obvious reasons. And your assignment is about transient analysis. Analysing a circuit when you first turn it on and see what happens to it before it's at steady state is called transient analysis. And so you're going to get a circuit. You're going to come up with an equation that you're going to solve. You're going to solve it using Laplace transforms, which means you're going to end up with something that looks a bit like that. And then you're going to plot it on an autograph and see what the function looks like. So let's put this function into autograph. So start, autograph, and then type it in. So when you get to this point, you enter equation, and then you're going to type in y equals so I can write Q for charge, e to the power brackets minus alpha, and I can't use t for the variable, it only recognises x, so I'm going to have to substitute x for anywhere where t occurs, and then brackets, what was the rest of it? Cos omega t, cos w for omega, x for t, plus alpha, I've got an alpha available, divided by w for omega, sine w x, close bracket. Just to make sure it knows that it's a cosine of the whole of that omega x, put a bracket round it, and it's the sine of that whole omega x, put a bracket round it, and then hit OK, and we get the function. And then you can print this function out, but of course you can play with it before you print it out. You can shift it around using this hand tool. Okay. If you look at it, we can zoom out, by the way, and we see that on the left-hand side over here, actually, the function goes really strange on the left-hand side. Of course, this is a mathematical function, and what we plotted is a mathematical function. We're trying to relate this mathematical function to the real world, i.e. a model of a circuit, so we're actually not interested in any value of x less than 0, negative value of x, because it's time after we've closed the switch on the circuit, so therefore we're only interested in plus values of x. So the first thing we can do is shift the whole thing over here so we can ignore that. And then I need to see what's going on, so let's zoom in on the y-axis. And that means that I can expand out the function like this. Shift it down a bit. If it's all in a bit tight region, I can then zoom in on the y-axis to stretch out the function. And we get something like this. Now, you can see that actually, if we change the values of omega and x, which you can do, each of the constants that are in here can be varied. Look, alpha represents the alpha constant, q the charge, and w for omega. Q is the initial charge, and by default, all of these values are set at 1. Look, so alpha is set at 1, q is set at 1, and w is set at 1. Omega rather is set as 1. So the initial charge is 1, which is, you can see up there. I can change the value of the initial charge. That's not the interesting one. The interesting one is we try and change alpha and omega. If I change omega, that changes the rate at which it oscillates. Ooh, okay. Remember this axis here represents time. And
so are we saying that the inductor pushes back, so it pushes charge back into it?
It looks like it, doesn't it? Because of this part down here.
Yeah.
Yeah, that's right. So yeah, that's the question I was asking, really.
So it actually charges up the capacitor.
Yeah, because that back EMF creates a voltage which is trying to push the charge the other way.
Yeah.
So it manages to for a short period of time.
Yeah.
And then the capacitor starts to discharge again, and then, but it's an oscillating.
Yeah.
So it dies away.
Yeah.
We can change the value of alpha. And if you look at the original function, which is here, no, that's the solution. If we look at the original function, alpha is the constant inside this exponential function, so changing alpha should have an effect on the rate at which it decays this charge. So if we look at alpha in autograph and decrease alpha, then we find the rate at which this thing decays gets less. So if you look at this function, I was doing so well. Bit of editing having to go on here. If we look at this function, we can see that we've got an exponential decay envelope, if you like, and within that envelope we've got an oscillation. So those are the two components for that function. Now, by analysing this circuit, let's just close this. No. Do that. I want to do this. Put this into the notes. There it is. So yes, by what was I about to say? Yeah, by changing the values of alpha and omega, we're effectively changing the values of R and L and C, because if you look at the definitions of alpha, A and blah, 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 right, so effectively, by changing the values of R and L and so on, we can change the rate at which this thing decays. By changing omega, we can actually make sure this thing's going to die away pretty quickly. And we have an effect of something called critical damping, which Mike was mentioning this morning, where you want this circuit to just very quickly, any oscillation to die away. So you can change your values of R and L and omega with L and C, so you can change the values of L and C until we get this effect. Okay? So that's the sort of function that we're aiming to look at here. Now I don't want to say changes to that. I've got this. So that's our function, our solution to the differential equation, which allows us to analyse this transient theory, after which we get this steady state of zero. Right, Andy? Yep. Good. Take a slug of water or something. So, just a quick recap. We've got the circuit, okay? If you're going to go to close both eyes. It's very disconcerting. So, yeah, we've got our circuit.
I'm just supposed to get a copy, that's why.
Don't blame me. So we've got this circuit. We want to come up with a function that means we can describe the circuit. How do we come up with a function? We write a differential equation which describes it. Okay? And you'll get something like that. You'll get this. Well, that's the first step. So come up with this equation that we can then solve, and that's where the Laplace transform starts. And then when we've done that, we solve it. We come up with a function which allows us to describe the circuit, and there it is. Okay? Right. So now a little bit of maths for us to get our teeth into. How do we get from the ordinary differential equation to the solution, was the question Mark was asking. How the heck do you get from that equation to that solution? We use Laplace transforms.
So Laplace transforms a mathematical tool as opposed to an electrical tool.
It's a mathematical tool.
So are they using other things
Oh,
other
yeah.
than... Right, okay.
It's a mathematical tool to solve an ordinary differential equation. Differential equations can arise in all areas of engineering. So it's not just for circuits. You should have, or it might be yep, you've got your handout. If you turn on the course notes to page 5, you see a table of the standard Laplace transforms, and there they are. Okay.
What?
So generally, solving ordinary differential equations, ODEs, involves integration. Why would that be a true statement? Why is that an obvious statement?
Involves constant sign.
No, that's not the reason. An ordinary differential equation involves a differential. So how do you undo a differential? Integrate it. The opposite of differentiation is integration. So to get back from a differential to the original function, we need to use integration. Integration techniques involve trying to get an integral to look like a standard integral. In a table. At the end of the day, when you're doing integration, you look up the integral in the table, don't you? The table is standard integral. If the integral you're trying to do doesn't look like a standard integral, then all the techniques that we've looked at to do with integration are all about trying to get it to look like a standard integral. If you cast your mind back, at the end step of all of those different techniques, we look up the integral in the table to get the solution. The use of Laplace transforms is just an extension of this. So that's our table, like our table of standard integrals. That table in the course notes on page 5 is a table of Laplace transforms. That table of Laplace transforms is like your standard integrals. Okay. To use them, one, transform, hence the name Laplace transform, each part of our ODE into a function involving a new variable S. Sometimes we say we're transforming into something called S space, a new area to work in, involving a new variable, which actually is just a sort of an integral that's being done for you. It's like we're using an integral that's already been done, playing around with that, and then transforming back from that integral into the original form. So first of all, we transform each part of our ordinary differential equation into a function involving a new variable S. This is like doing the integration. And then we manipulate it, and that's the fun bit. The function in S space using algebra to get it to look like one of the S functions in the table.
That's all like a perfect square.
Yeah, that's when we use things like the perfect square then to do that. Yeah. Manipulate the function in S space using algebra to get it to look like one of the S functions in the table, and then 3, transform back to get our solution. So in other words, there's no integration involved. We're sort of swapping integral calculus for algebra. So we're just changing it to a new form so we can just play around with it algebraically and then changing it back again. We don't need to do an integral. Because by changing it into a new form, that's sort of like doing the integral bit, which has already been done for us, effectively. I've oversimplified it slightly, but for the purpose of this assignment, for this course, you know, I've oversimplified the process, like, should I say. We could go into a lot of details how these S things are arrived at in the first place, and if you're interested, there are some handouts I can give you on them, which show you how you get your function from, for example, the left-hand or the middle column in our transform, something like AT squared, for example. Y is the Laplace transform of that 2a over x cubed. It's to do with the integral between 0 to infinity of some sort of exponential function. And if you're interested, you can have a look. But basically, all we need, it's a bit like the standard integrals. Once you've done it once, and you've got that solution, that's all been done for you. You don't need to do it again unless you're interested to see the mathematical process. After that, you just use them. And that's what we're going to do. Okay, I'm trying to make it simple for you. Step 2 involves algebra. Did I go too quick for you, Mark?
No.
Step 2 involves algebra, and in particular, as Liam says, the perfect square is a technique we're going to be looking at today, and 2, something we've already looked at in the past, partial fractions. So they're going to rear their ugly head again. That's for another time, though. We're going to start by having a look at this perfect square today.
He's going to do it anyway, we're from no.
No, actually, I wasn't. You just reminded me, Liam. Okay.
This is missing.
Okay.
What?
Right, let's have a look at the perfect square then. Right, David. X plus 2 squared. If I were to expand that out, what would I do? I'd do x plus 2 times x plus 2, because it's 2 squared, agree, David? Now, multiplying out as brackets, I have to multiply every term in this one by every term in that one. So I would get, let David carry on. Yeah. Right. Can I simplify that?
Yeah. 4x.
Yep. That's a perfect square. Perfect square. Why is it a perfect square? Because it can be written like that. X plus 2 all squared. Can you expand that one for me, Mark, then? X plus 3 squared?
Yeah, that will be x cubed. So, x cubed. Sorry, no, x squared. Sorry. Yeah. Plus 6x.
6x.
Yeah, plus 6. 9.
9. Yeah. Okay, look at this. Imagine that was not a 2, but it was a 3. X squared plus 3x plus another 3x is 6x plus 3 is 9. Everybody happy, Andy? Yeah. That's a perfect square. This is a perfect square. Why is it a perfect square, Andy?
Because it can be written as x plus 3 squared.
Yes, all squared. Okay? Robin,
Yes.
can you do the next one for me?
Multiply it back.
Yep.
So that'll be x squared, isn't it? 8x plus 16.
Right. That's a perfect square because it can be written like that. Okay? Yeah. So, can you see the pattern?
Yep.
So, if you didn't know that was a 4, how did you arrive at that was a 4? Look at this. Look at this. Look at the top one. What's this one? Oops.
I know that one is.
Yeah. Why is it 7?
7 sevens are 49.
Right.
2 sevens are.
Yeah, it's half of this look, isn't it? Okay? And then whatever that half of this is squared. Agree, David? That's the perfect square. That's the perfect square. How would I get that to be a perfect square? What goes here and what goes there?
That'd be 2.5.
That'll be 2.5.
2.5 times 2.5.
Is
6.4. 25.
2.5 times 2.5? 6.25, is it?
2 points.
Have we got a calculator? Confirm that?
Yes, half and one. Yeah.
Yes, it is.
Okay.
25 looks like that.
Is that a perfect square?
Yeah.
Yes, because it can be written like that. So it doesn't have to be a whole number. A perfect square is one where we can rewrite this as this. Now,
No, doesn't work.
can I make it a perfect square?
Yeah.
What would I put in here?
4. And then minus.
Minus 6.
Minus 6.
4 minus.
What does this number need to be?
Needs to be 64.
So what have I got to do?
Minus 54. Oh, plus 54. 6 minus 6.
I've got to add 6 onto that, haven't I?
Yeah, minus 6.
To make it 16. So I'd have to add 6 onto here as well,
Right, okay.
plus 16. So in other words, I would add, let's see,
Yeah. Where did you get 52 from?
I thought, no, it's not 64. It should be 4.
yeah, it's not 8, it's 4, isn't it?
It's 4 plus 4.
It's half of that
Oh, yeah.
squared, isn't it? So half of 8 is 4, 4 is 16. So I'd have to add 6 to that side and add 6 to that side to make that 16 to make it a perfect square. Okay?
Yep.
Do this one for me.
No.
Convert that to a
Yeah, you
perfect
are, but
square.
you add it onto there, so you can add it onto the other. You need to add it on.
Minus 10.
These are the things we might shift.
Oh, yeah, Harry, I can see your point there.
You shift.
If I do x plus 4 squared, I'm going to get plus 16, so I need to take the 6 off to make it 10.
Six minus
Yeah, you did, yeah. Minus 6. Minus 6 equals x squared plus 6x. That's 8x plus 10. Yeah. So what about this one?
Well, that would be 5, because 5 plus 5
Yeah.
is 10. So we know that's 5, so it's x squared plus 5 squared, and then you've just got to work out what that bit is in the middle. Which is 5 times 5 is 25, is 15.
This time it is plus 15. Because we've got to make it 40. Yeah, thanks, Harry. You saved me dropping ourselves into that hole there. Okay? Now, if you look at your table of Laplace transport, okay? Oops, well, right.
Let's have a big look now.
If you look at your table of Laplace transforms, at the bottom two, if I'd done my solution to my solving my equation and I'd come up with this, okay. Okay. Oh,
Press the save button.
that's closing on me.
Red flashing light.
Where?
Red light green.
Where's the red flashing light?
We're waiting. Going forward. They all like flash. Go down when it is.
Oh, so we
Hmm.
That's what we call it. Just doing the laptop.
Right, maybe I just call something else out by
let's say what?
Okay, might be all right now. Orientate.
Right, yeah, if you tend to look for point, it's getting girly.
Yeah,
Yeah, brilliant question about.
So what would be pink rubbish?
what is it?
It's really? I never know, if I'd have known that before.
But that black one, boy.
Okay. There's a magic tool here that I've got, okay, that I can use to highlight certain areas. So if we've got as part of our solution, and wait for it, x squared plus 10x plus 40, okay, and I want it to look like, remember the purpose, so the last step of these Laplace transforms is to get it to look like one of these. And if you look underneath, at the bottom two, that looks like this, doesn't it? The bottom of the fraction on the bottom two of those Laplace transforms, the final column on the right, the bottom two, s plus b all squared plus omega squared. And it looks like this, s x plus 5 squared plus b.
The bottom of the class.
Yeah, just the bottom here, that's all we're doing. Okay? So in other words, as part of the process, you remember I said to you we're going to be using algebra to manipulate these things to get them to look like these transforms. And one of the tools we're going to be using is the perfect square. Well, here it is. We've used the perfect square to rewrite this like that so that it looks like one of these in here. Okay. So let's look at another example. If, as part of my solution, or as a solution to a circuit in S space, we get 5 over use the perfect square to get this to look like here.
Defines the solution.
To a circuit in S space, we get this
S space or S space?
S space. This sort of idea of S space. We're in a Laplace transform.
I thought it was base.
No, S space.
Base.
Use the perfect square to get this into the form A omega over S plus B squared plus omega squared. And then identify A, B, and omega. So, do you want to have a go and have a look at it together? So if I give you a few minutes, you can have a go. A little bit, certainly. Is that far enough?
Just to the top of that. Yeah.
what I'll do is I'll hit pause and we'll
Yeah.
okay, so focusing on denominator first, looking at this, we've got x squared plus 7x plus 26, which making that to a perfect square, half of 7 to get 3.5. 3.5 squared is 12.25, so we need to add another 13.75 to get that. So we can now identify some of the terms we've got. If you look back to the original question, b is 3.5 and omega squared equals 13.75. So b equals 3.5 and omega squared equals 13.75. So therefore omega is the square root of 13.75, which is 3.71. It's a pretty significant figure, presumably. Now we've just got a problem with the topic, right? 0.8. And how have you done that, Harry? So looking at the top bit, now for the numerator, okay, we've got the A omega equals 5, haven't we? And so omega we now know is 3.71. A times 3.71 equals 5. So A equals 5 divided by 3.71, which is 1. Now, just to finish off today,
Sorry, can you just go up?
Yeah,
Just
yeah.
checks. No touch more, please. Yeah, that's fine.
now look at the solution. Looking back, what solution gives us that? A damped cosine wave, which is a e to the minus bt cos omega t. So this transform gives the solution a e to the minus, oh, actually, sine wasn't, a e to the minus bt sine omega t. And so we could just plug in our values. So the function involving time equals a, which is 1.35, e to the minus b, which is 3.5, t sine omega, which is 3.71 t. And that would be our function that we would then plug into autograph and we'll describe. Yeah. Not long to go.
What's that? Oh, right, you've just got the figures in.
Yeah.
Right, ft equals. Right.
I might just have to present that solution because I forgot to put the microphone on.
That's probably good.
So let's just finally just quickly recap and have a look back here. Analysing circuits using Laplace transforms. So, Andy, what are Laplace transforms used for?
Washing the dishes.
It's an addition to ensure.
Yeah, what are you used for?
It's to solve the mathematical model.
Yeah, exactly. To help us solve a mathematical model, and the mathematical usually involves a differential equation. So we use mathematical Laplace transforms to solve differential equations. What are they?
Difficult.
Difficult, Mark. What are they? What is a Laplace transform? It's difficult to put it to work.
Laplace transform is where you basically transform it into a form which is easier to manipulate and then transform it back.
Exactly right, Mark. Thank you. Yeah, well put. Okay. Transform it into a new form that's easier to manipulate algebraically. So we're doing algebra rather than integral calculus. And then at the end we transform back, which is what we've just done. How do we use them? Well, Mark's just and we've got an example where we've actually used one to end up with the result. Okay. Okay. So do that again.
Thank you.